I have two research seminars. The first one given by Dr. Najar from Kairan, that's in Tunisia. And you can all see the title and see what he has to say.
Okay, thank you. First of all, I would like to thank the organizer for giving me the opportunity to speak here. My talk is about localization of random divergence operator. It will be organized as follows. I'll start by introduction and giving the model. After that, I'll try to define the integrated density of states and giving some results about that. And finally, I'll try to give some application of our results to get localization. For our model, explicitly, we consider the random divergence operator having the following form, which is the form which is given in the lecture of Pasteur. When we take this is equal to the identity, we get the Laplacian. And here we consider a omega is an elliptic d by d matrix valued, which is a d ergodic random field, and such that there exists some constant rho star which is bigger than 1, satisfying the following inequalities. H omega describes a vibrating membrane in the random medium, and in the particular case when we consider a omega as rho omega times the identity, and here the identity matrix, and rho omega is a real function, we get which is called acoustic operator and considered by Figutin and Klein and other papers. And to give the model explicitly, we consider a omega as an Anderson, having an Anderson form. That means that it's the form A0 psi plus that quantity which is having the Anderson form, and we consider as we have some perturbation of some periodic matrices, where here A0 is periodic, which is also uniformly elliptic, and omega gamma is uniformly a family of random variables which are independently and identically distributed, taking value in.
Could you maybe show again previous formula just to see?
Yes.
So your random piece is just this sum, second sum, right?
Yes.
And these omegas are random plus minus ones?
We have a family which is R in ZD.
Okay.
Of random variables, and we consider the Anderson form, and as we have some perturbation of some periodic matrices, and we suppose that the common probability measure is supported in the interval 0, 1, and we do the following assumption on the probability that omega 0 be in the interval 1 minus epsilon, and epsilon, this quantity equal to minus kappa, with kappa is some constant in 0 plus infinity.
Stop.
Sorry.
What's the meaning of it? Just to understand. What's the meaning of this?
We mean that the probability behaves as exponentially minus.
So when omega is close to 1?
Yes, it behaves like.
When approaching 1, it approaches it with this rate.
Yes. We allowed it to approach with this rate, and there is many assumptions done, because here we allowed it to decrease exponentially. Right. Because there is many assumptions where we have to get Lifshitz ties, we have to that this quantity does not decrease exponentially.
This will be used to show some Lifshitz tail.
Yes, yes.
Just to know where you.
Yes, and B will be a matrix which having two possibility behavior. The first one is this behavior, which we call it locally decreasing which is sufficiently decreasing as a polynomial, and the which is call it short range matrices. And the second possibility is to take a long range decrease. That means that for the first, it depends in which B decrease polynomially or are switched between two polynomials. There is two possibility that we have a fast decrease or more than polynomial decrease. Here we will define our operator. We consider H omega to be the following quadratic form, which is defined for U in H1 RD as the scalar product we consider in RD A omega minus 1 nabla U psi, and we take the bar to get a closed symmetric and definite positive quadratic form. We consider the operator H omega as the self-adjoint operator associated to this quadratic form. If we consider for any gamma in ZD, we set the translation by gamma is tau gamma, then tau gamma for gamma in ZD is a group of unitary operators on L2 of RD. And for any gamma in ZD, we have this equality, which means that H omega is a measurable family of self-adjoint and ergodic operators. Now we have the theorem which is given in the lecture of Pasteur that because of our assumption on ergodicity, we know that there exists sigma and sigma PP and sigma AC and sigma SC, which are non-random and closed subsets.
These are spectra.
What?
These support. These are components of the spectra.
Yes, yes. There exist some sets which are closed and non-random subset of R, such that sigma is the spectrum of H omega with probability 1, and if we denote by sigma PP and sigma AC and sigma SC, design the pure point spectrum and the absolutely continuous spectrum and singular continuous spectrum of H omega, then we have a non-random part of each component. Now we will define the integrated density of states. We consider our operator and we let H omega LD be the restriction of H omega to the box. The definition of the integrated density of states that I will give, it will be the definition of any other operator. It's not a divergence form or Laplacian. If we take a random Schrödinger operator and we take its restriction to a box of size L and define the quantity as 1 over the volume of L times the number of eigenvalues of H omega LD, which are smaller than E. This quantity is well defined as if we consider, for example, the Laplacian or the divergence operator. They are elliptic operators and.
Question?
Yes.
Is D for Dirichlet bound?
Yes. D to say it's a Dirichlet boundary condition, but we can take a Newman boundary condition or periodic one. What is necessary is to consider self-adjoint self-adjoint boundary condition. As we deal with elliptic operator, when we restrict the operator to a bounded region, that operator will have a resolvent which is compact. So we have a discrete spectrum with the possibility of accumulation to the infinity. So for any fixed E, thus this quantity is well defined. When L go to the infinity, this quantity converges. The limit denoted by NE and is non-random and independent of the boundary conditions, it's called the integrated density of states of H omega. What we do here, we take the restriction of our operator to some bounded domain to, for example, we restrict it to gamma L. With the restriction to L2 of gamma L, the operator will have only discrete spectrum. So we can, for any fixed E, we can quant the number of eigenvalue, and then we normalize with the volume, and after that we let L go to the infinity and the limit exists. So to prove, for example, the existence, we can use superadditive ergodic theorems, and now we will deal with the behavior of the integrated density of states, which we note N. We will recall the conjecture of Lifshitz, which was done in 1964, that for random Schrödinger operator of the form, if we take, for example, this form, N should behave like NE exponentially minus E minus E0 exponent minus alpha when E goes to E0, and here E0 is a fluctuating edge of the spectrum, and alpha is some positive component, which we call it Lifshitz component. What we here conjecture that if we take, for example, here A0 is the bottom of the spectrum of the Schrödinger operator, the integrated density of states should decrease exponentially fast near E0.
I just don't know, just for general education. What means fluctuating age? That it's not non-random in the limit? That it
Fluctuating edge, that means that it's an edge which is not stable. That means that it depends on many realization of omega.
was not, it's random quantity even in thermodynamic.
That means that it's sensible to the randomization, yes?
So are you getting this the bottom edge of the spectrum of the upper one? Because your conditions on the random variables were somehow near 1, right?
He's in the continuums. I believe there's no upper edge.
Yes.
There's just a lower edge.
Yes. And here, just I give an example because the conjecture first was given for Schrödinger operator of that form. So, for example, if just an idea before I give some results which are proven for the Lifshitz conjecture, that if we consider, for example, Laplacian, and we take, for example, the omega having the form of Anderson. That means that if we take this, for example, with is positive, and omega gamma is a family of random variables, which here, as we take, for example, a light, and at each point, if, for example, in 0, if we have this, in another point we have this potential, and it depends on the value of omega gamma, which, for example, takes value in 0, 1. For example, if we take is positive, the spectrum, we can get that the spectrum of omega is 0 plus infinity, for example, and the bottom of the spectrum will be equal to 0. And the conjecture of Lifshitz said that the integrated density of states should decrease exponentially near 0. If we want to say to know why he said that, for example, if we consider the equation of eigenvalue equation and try to change with this, and using the scalar product, we find that should be in the following form to A, for example, if we take the norm is equal to 1. But if I deal with the bottom of the spectrum, that means for E small enough, this should give two things, that is less than E, and also as we deal with positive potential, smaller than E. As we can consider the restriction to some cube of tie L, that means here we consider the sum over gamma in gamma L. For E to be small, we have for almost all gamma in gamma L, omega gamma should be small. So we have this with probability exponentially minus C over or times the cardinal of gamma L. But to construct, for example, eigenfunctions such that are eigenfunction of the Laplacian with which are smaller than E, for E small enough, we need much more space. And L should be like
And this is alpha 1/2.
yes, and this is, if what is this, it will be for D dimension, and this is the Lifshitz exponent.
So E naught here is well defined, it's 0.
Yes.
In this example.
Yes, in this
So
example
it's
it's 0.
fluctuating as
Yes.
well, it's just
No, 0 is for random Schrödinger operator, it's fluctuating edge.
yes, but you see, then the left hand side of this formula is just deterministic, and of E is deterministic. So right hand side also should be deterministic in this sense. But on this example, I understood.
Okay. So for alpha, it could be equal to minus D over 2 or other thing. That means that what we expect that each n should behave, for example, near 0 as for some positive alpha, which means that we have exponential decrease. I'll give some now result for this conjecture. It was proved rigorously by first for E0 equal to the bottom of the spectrum of random Schrödinger operator of the form of 3 that is given, by Pasteur and Nakau in 1977. After that, by Kirsch and Martinelli in 1983. For analogous discrete Schrödinger operator, that means that we consider the same operator in L2 of ZD. There is the result of Kirsch and Simon in 1985 and 86. For E0 internal edge, it's not so easy to do it. Also in this case, it's not so easy to do it. But for the internal edge, it's more difficult. And we have the result of Mezenscu in 1986 by Simon in 1987 for discrete Schrödinger operator. And for the continuum case, we have the result of Klopp in 1998. For acoustic operator, that means for random operator in divergence form, we have for E0 equal to 0, the bottom of the spectrum, we have the result of Kozlov in 1970. We have not more than the polynomial decrease. That means that the conjecture, it's not true at the bottom of the spectrum, and this is we can deduce this easily as if we compare our operator to the Laplacian. We have the divergence operator, which is minus Laplacian, and for E0 equal to 0, we know that this decrease only polynomially fast in 0 because there is no randomness here. So for E0 equal to 0, for the divergence operator, we can't expect to get Lifshitz ties. We have only a polynomial decrease, as looks like the free Laplacian, and there is no randomness. And we say that E0 equal to 0 is a stable edge for the divergence operator, even with random potentials. For E0 internal edge, I proved that there is Lifshitz ties at
What means internal edge?
yes, I'll explain this. For the spectrum of an operator could be of the following form. For example, for some periodic operator, we have
Gaps in spectrum.
yes, the spectrum having this form. That means there is gaps on the spectrum. For the internal edge, are edges which are inside the spectrum. So to prove result or to define the result, we have to consider in general our random operator as a perturbation of some periodic operator. We set H1 equal to this quantity. This is nothing but the operator when we take all random variables equal to 1. And what we get here is the same operator, but here omega gamma equal to 1 for any gamma in ZD. That means we take any random variables equal to the extreme value, which is equal to 1, and we get a periodic operator. So we can write H omega as H1 plus delta H omega, which is delta is some positive. By this, we consider our operator as a perturbation of some periodic operator. In general, we want to, if we have some random operator to study, it's convenient to consider it as a perturbation of some reference potential reference operator which is not random, which is, for example, periodic in our case. And we consider this. This is having the same form as a Schrödinger operator. The problem that here it's not a simple perturbation. Here we have an operator of the same order as H1.
It doesn't look symmetric anymore. Is that?
Yes, it's symmetric. Yes.
You forgot to write a U somewhere.
What? Yes. Yes, there is U here. Yes, I'm sorry.
With the U, it's symmetric.
Yes. And for any gamma in ZD, we say it, so just we change the random variables. We note that H1 is ZD periodic operator. We denote N its integrated density of states by just small n. We do the first assumption that there exists E plus positive and delta prime, which are positive also, such that the spectrum of H1 cap this interval is equal to this interval. And we suppose that sigma H1 cap this equal to empty set. This is what we suppose, that there is a gap below E plus, unless it's not having meaning to study internal Lifshitz ties. So we have to do the assumption that there is a gap for the periodic one, which is preserved after perturbation. So what we do, we suppose that, for example, we write that H omega equal to H periodic operator plus, we suppose that the spectrum of H periodic having the following form, with a gap below some point E0. Here we suppose that E0 is positive strictly because we know that E0 equal to 0, it's not a fluctuating edge, and we can't prove Lifshitz size near this point. So for that, we exclude the point E0 equal to 0 in our assumption, and we suppose that, for here we start in 0, we suppose that the spectrum of the Al-Masur spectrum of H omega starts, for example, after perturbation. It still starts by 0, and there is some gaps which will be closed after perturbation. For example, this could be shrinks like that. But what we ask that there is some delta positive, and after perturbation, even E0 still a gap.
A question here?
Yes?
Do you want E plus to be an eigenvalue or not?
We want that E plus be in the spectrum.
So it's in.
Yes. So we suppose that after perturbation, there is still a gap below E0. We will do a remark, the existence of open spectral gaps, because here we have supposed many things. We have to verify if our assumptions are verified for our operator. The existence of open spectral gaps in the spectrum of certain periodic acoustic operator for D equal to 2 and D equal to 3 is studied by Figuten and Cushman, and it's proved that it's possible to get a medium in D equal to 2 and D equal to 3, which verify our assumptions. And the band gap structure of the spectrum of the elliptic operator in divergence form for D bigger than 2 is considered by Hempel and Post, and it's proved that for divergence operator with periodic coefficient exhibits some gaps inside the spectrum. So now by adding a disorder parameter G in the equation which define H omega, that means this equation, here it should be A omega. We can choose G small enough so that the spectral gap in sigma H1 will not be closed after perturbation. That means that also this assumption is true. That means that we can add another parameter here and choose it such that this assumption holds. So our assumption makes sense. The first result that we give is concerning that if we consider H omega be the random divergence operator, we assume that A0 and A1 holds. The first theorem is if B is short range type, that means that decreased polynomially, for example, or compactly supported, then this N is the integrated density of states of the periodic operator, which is H1 or H periodic, equal to D over 2 if and only if we have Lifshitz ties near E plus with this component. And this is kappa is the disorder. Yes, it could be equal to 0, for example, or in literature, in general, we take it equal to 0.
Excuse me?
Yes?
B was this a random part of your operator, right?
B is the...
B is like the potential.
yes, like the potential U. B is like this U.
Yeah, these amigos. Yeah.
Yes.
Could you just remind me, because it was some time, this kappa appeared in some condition?
Yes, this kappa is just that the probability does not decrease exponentially fast.
So it reappeared.
Yes, it reappears here for that. This there is not so enough results that links that, because in general they take it 0. In general, the first result appears for Lifshitz ties, for example, for Schrödinger operator, are under some assumption that, for example, here the first assumption was done by Kirsch that the probability that omega 0, for example, in the interval or in 0 epsilon is bigger than alpha. That means that not decrease faster than a polynomial. After that, we have better result. We have the limit sup of log of this probability over log epsilon equal to 0. That means does not decrease exponentially fast, which generalize this result, which is better than this result. And now we suppose not the limit sup, but the limit is equal to some minus kappa. That means that we have more control on the disorder. So we have this in the short range case. If B is of long range type, then just I would like to do some remark here. Here we link the behavior of the integrated density of states with the periodic operator, which is the background operator, with the Lifshitz exponent. That means that's equal to d over 2, which we say that is the integrated density of states of the background operator is non-degenerate, if and only if the Lifshitz exponent is minus d over 2 plus kappa. But it's possible that find when we have not this assumption, but surely the exponent will be not equal to minus d over 2 plus kappa, but it will be alpha equal to this quantity if and only if for the periodic one we have this limit. For B is of long range type, then we have, if we have polynomial decrease of the integrated density of states of the periodic operator, then we have Lifshitz ties, but it depends on kappa d over 2 plus kappa and d over nu minus d, which this quantity is the as in long range type, we ask that B does not decrease faster than the polynomial of this exponent. So it will depend, for example, if d over 2 plus kappa is bigger or smaller than this quantity. If we have kappa plus d over 2 is smaller than this, so we can omit this assumption, and we have Lifshitz ties without any assumptions. Some comments of the result. Here the behavior of the random variables is linked up to Lifshitz exponent, determines if we deal with the classical regime or a quantum one. That means that if the kinetic energy intervenes or not in the Lifshitz exponent.
You mean, just to try to understand this, you mean that if everything is determined just by decay of purely potential, or it's modified?
Yes.
Okay.
Yes. In the Lagrange case, Lifshitz exponent depends on the value of kappa. The Lifshitz asymptotics are classical for kappa smaller than this quantity, or quantum for kappa is bigger than this. That means if it's governed of the uncertainty principle or not. Indeed, the Lifshitz exponent depends on the uncertainty principle. That means on the kinetic energy only in the case when we have this. In contrast, when we have that quantity, that means that kappa plus d over 2 is smaller than the decrease of the potential. The Lifshitz asymptotic are not governed by the same consideration. For d smaller than 2, assume that B is compactly supported, and assumption A0 and A1 hold. A0, that means we have the model of Anderson, and A1 we have this. There exists alpha positive such that we have Lifshitz ties with some exponent alpha which we do not compute, which we know that they exist, without any assumption on the behavior of the background operator. And this result is proved only for D. For D smaller than 1, it's already known that for divergence operator and for Schrödinger operator, the integrated density of states of any periodic operator is non-degenerate.
Smaller than 2.
Yes, for D equal to 1.
Equal.
Yes, for D equal to 1. We know that the integrated density of states for a periodic operator behaves like which is we say that we have non-degenerate integrated density of states, but for D equal to 1 and 2, for D equal to 2 we prove that there exists, but the exponent alpha it's not, for example, minus D plus kappa, because we proved that this alpha equal to that only and only if we have that. So surely if we consider to D equal to 2 and we know that the integrated density of states of periodic operator does not or it's not degenerate, surely alpha is different of minus D over 2 plus kappa. Application, localization for random divergence operator. If you consider H omega the operator defined by 1 and assume that A0 and A1 holds, and we have a Wegener estimate, that means that we have certain control of the probability that the distance, for example, of H omega restricted to some box smaller than epsilon, this probability is smaller than the volume of this cube time epsilon exponent n. We have the following theorem. There exists epsilon 0 positive such that sigma cap I plus plus epsilon 0 equal to sigma pp cap I plus plus epsilon 0. An eigenfunction corresponding to an eigenvalue in I plus plus epsilon 0 decays exponentially fast. And we have more. For any p positive, we have this quantity is finite. And what we prove? We prove that under our assumption, near this point, there exists an epsilon 0, which the spectrum here in this interval or E plus is Peer point. That means that we prove that we have Peer point spectrum in that interval, and we have
Question.
yes.
Could you please show the slide before where you stated the condition? I didn't get that this week.
This
Yeah. So, what is this actually?
This is what we call the Wegener estimate. That means that what explained Spencer the morning, for example, we have two things to get localization. We have Lifshitz ties and another repulsing of level. The Lifshitz ties is given by the theorem, and the assumption of repulsing of level it's given by the Wegener estimate.
Just the existence of smooth density, I understood that Wegener estimate. No?
What?
I thought that the Wegener estimate, just as we were told yesterday by Pastor or by whom? Pastor. It's just the existence of smooth density.
If we have smooth density, we have Wegener estimate.
Yes, that's.
But here, why we assume that there exists? Because in my model, I didn't assume that the probability has a density, for example, or the probability is Holder continuous. If we suppose that the probability is Holder continuous, it's proved that the Wigner estimate is true. Is it clear?
Okay.
It's
Thank you.
some regularity of the density.
So the first point and the second point are known as Anderson localization. We say that we have Anderson localization in the interval E plus plus epsilon 0. That means that the spectrum in this interval is pure point, and any eigenfunction corresponding to an eigenvalue in this interval decreases exponentially fast. The third result is known as dynamical localization, and here what is pi I is the projection, the spectral projection on the interval I plus plus epsilon 0. And here k is the characteristic function of k is and k is any compact subset of Rd and X a position operator. If we have this, and for example we start with some eigenfunction corresponding to this interval, and the dynamic of this operator can't go to the infinity, that we have a big ball that the wave function is confined in a ball of radius big R, but is finished. If we start by an eigenfunction which are corresponding to an eigenvalue which are in this interval. Because if we try to, for example, to solve the wave equation corresponding to the divergence operator, the solution are square h E1. If we start, for example, the solution of that equation are of that form, if u0 and u1 are exponentially decreasing, that means that they are eigenfunction corresponding to eigenvalue in this interval, this function will be localized in a ball of radius big R, which R is finished. Just because it's time, just a remark that this technique is also true for the Maxwell operator, which corresponds to the magnetic, not the magnetic, but the Maxwell operator, which having the same form. Yesterday we see with Sheikhan that she has proved that we have the same thing in one dimension in the past session, but I think analytical argument that we give it still work for Maxwell operator. Thank you.
Just a couple of questions.
Yes.
Your second statement about the exponential decay, what do you exactly mean by this? Is it some, so 3 is already some form of exponential decay, but what is the second?
The second, here we have an exponential decrease in space.
What does it mean? So do you know that there is some lambda, so that the solution can be bounded by E minus lambda x, or do you know that it is super polynomially decaying?
No, because for this operator, as it was done in the lecture of Pasteur, it's known that he has generalized eigenfunctions, which are polynomially decreased. It's proven that the divergence operator has his eigenfunction decreased polynomially, generalized eigenfunction. And we prove that using the decrease of the Green function That means the resultant, we can deduce that the eigenfunction decreases exponentially fast.
So can you control the power of the exponential or not?
There exists some gamma positive, which we know that there exists. The proof of such theorem is known, but we need multi-scale analysis to prove this theorem is proven. After the work of Froelich and Spencer, we have to try to find two estimates, the Wegener estimate and the initial length estimate. The Wegener estimate is already known for this operator, and I do it as assumption here. Just, we have to, if we want to prove a Wegener estimate, we have to assume that the probability measure is Hölder continuous. But for the initial length estimate, we can use Lifshitz space to get the initial length estimate. And with the initial length estimate and the Wegener estimate, we can carry on the mid-scale analysis.
All right, so one more.
Do you know any relation between the density of states and this parameter of disorder kappa? Can you find out?
The density of states, it's the derivative in distribution sense of the integrated density of states.
No, but if you only the pure point part of the spectrum that you showed, that is the density of states increase or decrease when you increase disorder, or doesn't change?
It will increase. If you increase disorder, the exponent will be bigger. So as we have exponentially decreasing, it decreases more. Just we have this relation, for example. So if you increase kappa, this is decrease exponentially.
Okay, so let's thank the speaker again.